Hi friends, in this class we will study the module 3 topics, that is linear programming problems. Module 3, module 3 linear programming problems, or in other words, linear optimization problems. Both are correct. A linear optimization problem. Optimization problem. So in the previous module we have discussed the non-linear optimization problem or non-linear programming problems, right? So we know the nature of our objective function in a non-linear optimization problem, and also it is to be noted that there are no constraints we have discussed while discussing the non-linear optimization problem, because that is unconstrained non-linear optimization problem. So that is why we didn't discuss any constraints. So but in this session we will discuss the linear programming problems with constraints. So we will define some basic terminologies, so that you will get the clarity about the module 4 and the upcoming modules very effectively. So, linear programming means it is a mathematical programming technique. Actually, it is optimization problem to optimize the performance. Optimize the performance means, while we discussing the nonlinear optimization, we have discussed the objective functions, or objective is to maximize the profit and minimize the cost, like that. Like your fuel cost in the case of unit commitment, and also in order to minimize also the losses. Okay, and the yes, so like that. Okay, but that is actually non-linear in the case of unit commitment and fuel cost as objective functions. Now in this here we will discuss the linear objective functions. Okay, and for example, you imagine profit or cost functions, profit functions, and under this is subjected to a set of resource constraints, a set of constraints which is we call our engineers, we the engineers will call it as resource constraints simply. Okay, and the resource constraints, for example, we have machine hours and man hours, then money, then materials. Okay, like that. And in the case of power system, you have a lot of inequality constraints, and also equality constraints also, like maximum power to be generated must be less than the capacity of the power plant, the unit, and the minimum also there is a minimum limit also for the unit commitment of a unit in a power system generating power station. And this the a linear programming problem will contain a linear programming problem, that is LPP. LPP contains contains mainly one, like our nonlinear optimization problem, we have objective function. Objective function we should have, and then we have set of constraints. Set of constraints, so that we will discuss in detail. Then third, we have non-negative restrictions of decision variables. Non-negative. Non-negative means positive. That is, yes, greater than 0. Non-negative restrictions of decision variable. Decision variable. Yes. So these are the three components or three terminologies that we will come across. First of all, the decision variable. What do you mean by a decision variable? A decision variable is used to represent the level of achievement of a particular course of action. So I will give you the notes. This is just the definition, okay? And then we'll get into the problem. Then we will understand what do you mean by decision variable. And then the objective function, you already studied that. It is an expression representing total profit or cost. That means in the case of profit problems, cost problems, it is an expression representing total profit or cost. But it can be anything in the engineering field. It is not only the profit and cost. Okay, in engineering it can be anything, like minimizing the power loss. Okay, it can be that also. So the expression representing the total power loss in a power system, that can be an objective function. Okay, so like that. Then objective function will either maximization type or minimization type. Okay, and the objective function is a linear function of the decision variables of the form f of x. Yes, f of capital X. That means x is a vector, right? Okay, then that's equal to c1 x1 plus c2 x2 plus etc plus cn xn. So the decision variables are this x1, x2, x3, x4, etc. xn. So that means it is nothing but simply our variables. Okay. Yes, that means solution we have to find. So that's it. Then where ci, in general I am representing ci, where I varies from 1, 2, 3 up to n, and this ci are called the coefficients of cost or coefficients of loss function, coefficient of profit function, like that. Coefficient, just simply in general you can say it as coefficient. Then we have maximize. Example, yes, maximize f of capital X equal to 250 x1 plus 400 x2. This is the best example for a linear optimization problem, linear objective function, that is x1 and in x1 and x2 two variables there are, and this is the linear function, right? Okay, why? Because there is no x1 into x2, or you know that the non-linear function. What do you mean by non-linear function that we have? learned in the previous classes. So yes, yes, if you have any doubt, you can go and refer our very first video of this optimization. Okay, that is introductory class. Then we have the constraints, right? Subjected to the constraints. So what do you mean by constraints? What do you mean by these constraints? Constraints. A constraint is a kind of a restriction on the total amount of a particular resource. Constraints. Okay, that means constraints in the case of profit profit maximization and cost minimization, or maximization, profit minimization, or like that. We have uh, the constraint is defined as it is a kind of a restriction on the total amount of a particular resource. That means you have you have a power plant, and it has got five number of units, generation units. So that means it has P1, P2, P3, P4, and P5. Actually, these are the unit commitments. Suppose let us say that these are the unit commitments. That then this P max 1, let P max 1, P max 2, P max 3. All these are the maximum power that can be delivered by each and every unit. So in that case, the P1 unit commitment P1 must be less than or equal to P max 1. Right. So this is a constraint. Okay. That means a restriction on the total amount of a particular resource. Okay. A restriction, that is a limit, upper limit or lower limit like that. So it can be of three types. Can be of three types. That's it can be less than or equal to, like our uh, this constraint. Okay, constraint, and it can be greater than or equal to, like, yes, P1. And also there is another constraint associated with the unit commitment, that is P1 must be the unit commitment by a generating unit must be greater than or equal to some minimum value, that is P minimum 1, right? So it can also be greater than or equal to, constraint can also be greater than or equal to, or it can also be equal to, equal uh, expression also, that is less than or equal to expression, greater than or equal to expression, and equal to expression. All these are types of three types of constraints. Now for example, we have example we have a11 x1 plus a12 x2 plus etc plus a1 n x n less than or equal to, or it can be greater than or equal to, or it can be equal to some p1. Okay, this is example. That's the example. Okay, so and now we are moving on to the standard form of LPP. Standard form of a LPP. Standard form of a LPP can be written as minimize f of x1, x2, x3, etc. xn, that's equal to c1 x1 plus c2 x2 plus c3 x3 plus etc. plus cn xn. That this f of x1, x2, x3, etc. xn can be written as f of capital X, where capital X is your vector, Okay, vector x1, x2, etc. xn. Okay, and the C1, this C1, C2, C3, C4, etc. C1 is is known as the coefficients. Okay, and x1, x2, x3, etc. xn are known as decision variables, and b1, b2, b3, etc. Okay, so I'm not defining this b1, b2. So this is the objective function. So now we have the constraints subject, that means subject to the constraints, subject to the constraints a11 x1 plus a12 x2 plus etc. plus a2 a1n a1n xn equal to b1. That means this is nothing but a linear polynomial function. Okay, so in LPP the objective function as well as the constraints must be in linear form. Okay, and a21 x1, the next constraint, second constraint is a21 x1 a22 x2 plus etc. plus a2n xn, that's equal to b2, etc. We have m number of constraints associated. So am1 x1 plus am2 x2 plus etc. plus amn xn, that's equal to b1 b2 etc. bm. So there are total m number of constraints. Okay, and also we have uh, another constraint. So in a LPP, the constraints can be equal expressions. That means expressions containing equality like this, and it it can also be greater than or equal to, less than or equal to. Okay, constraints can also be possible. And also in this problem, he has given that subjected to another set of constraints, that is x1, x2, x3, x4, etc. xn greater than or equal to 0. That means decision variables are positive values. Okay, so that's about this standard form of linear of a LPP, and this is the standard form. Right now I'm transforming this standard form into the matrix form, that is nothing but minimize our uh, LPP is converted into, in the matrix notation it is can be written as minimization becomes minimization itself, and f of x1 x2 is f of capital X, and that's equal to C transpose into X, where C is nothing but your vector that contains your coefficient C1, C2, etc. Cn. And similarly, our constraints can also be notated in matrix notation also. Okay, so the constraints can also be notated in matrix form like this, that is to subject to the constraints ax equal to b, where a is your a11, a12, etc. a1n, and etc. This is am1, where am2, etc. amn, and b is equal to vector for matrix b1, b2, etc. b1. Okay. Uh, and the also we have another constant, that is positive values we are all taking. So x vector x is greater than or equal to this is so this is the matrix notation. Now the characteristic of characteristic characteristics of LPP in standard form. Okay, so have the characteristics of the characteristics of characteristics of linear programming problem in standard form. In standard form. So why we standard form? So why we study the standard form is the answer is uh, the solution or the how to solve this LPP in standard in LPP is the first step is you have to convert your LPP in the standard form. Standard form we have discussed earlier. Okay, you have to convert your optimization problem or LPP. If it is not in standard form, you have to convert it into the standard form. So the characteristics of LPP in standard form are first of all, we have the objective function f of x is of minimization type. So in our standard form, we will always deal with the minimization problem. So the objective function, you should carefully note this point, that is the objective function is of minimization type. So minimization type. And the second important point is all constraints are of equality type. All constraints must be all constraints must be in equality type in the standard form of LP. Equality form, inequality for equality type. And all the decision variables are non-negative. That means all decision variables x1, x2, etc. xn must be, that is x must be greater than or equal to 0. So these are the 3 points you should remember before solving the problem. So that means if the examiner is asked to maximize some objective function, maximize some objective function f of x subjected to some constraints, okay, then subjected to some constraint x equal to b, then what you have to do is you have to make, actually this is not in standard form of LPP. Standard form of LPP is the objective function must be in minimization. The objective function is of minimization problem. The problem must be minimization. So you have to make it as minimization problem. So that means any LPP can be expressed in standard form by using the following steps, and the following steps are, first of all, the maximization of a function. If the examiner is asked to find to find the maximization of an objective function, then you have to convert it into a minimization problem, like the given f of x is equal to the examiner given it as f of x equal to c1x1 plus c2x2 plus etc plus cn xn. Okay, is your question. Maximize this. Okay, then this problem maximization of this objective function is equivalent to the minimization of the negative of the same function. That means we will convert it into a minimization problem. Why? That means if you have to maximize this objective function, then it is equivalent to the minimization of negative of this function. That is, minimize some function. Let us say it is f star of x, where f star of x, capital X, is equal to minus f of x, minus f of x. Okay, that's equal to minus c1 x1 plus c minus, sorry, not plus, minus c2 x2 minus c3 x3 minus etc minus cn xn. Okay, this is our converted standard form of LPP. Okay, then suppose we have if some of the decision variables, the next case can be sum of the decision variables, let us say xj, where for some values of j equal to some values of j, and xj is examiner given it as less than 0. That means negative values for xj for some decision variables are, that means some decision variables are negative. But in the standard form of a LPP, we should have all positive values for the decision variables. That means capital X must be greater than or equal to 0. So in order to, you have to replace, or you have to convert this also into our standard form. So what we will do is, we will replace the variable xj replace by xj dash. Okay, that's equal to minus xj. So that means you are multiplying LHS and RHS with minus. So what will happen is minus xj, okay, minus xj will be greater than or equal to 0. That means inequality sign will be reversed. Okay. So, and yes, that is our one of our cases. And another case is that, another possibility is that if one decision variable, let us say xj, is unrestricted in sign, that means it can take positive, negative or 0 values, then the variable xj can be replaced as, then in such situation the xj can be replaced as xj replaced by xj equal to xj dash minus xj double dash, that where xj dash is a positive number, or xj dash has positive values, and xj double dash is also having positive values, xj double dash greater than or equal to 0. then in such a situation xj can be negative, positive or 0 depending on the values of xj dash and xj double dash. That means xj dash is greater than xj double dash, and it is positive, then xj is positive. And if xj double dash, sorry, xj dash is less than xj double dash, both are positive values, then xj is negative. And if xj dash equal to xj double dash, then xj is 0. So it can have it can take positive, negative or 0 values, right? So we will, in such a situation, we will replace xj by xj dash minus xj double dash, where xj dash greater than or equal to 0 and xj double dash greater than or equal to 0. That means we xj is can take positive, negative or positive values, but xj will is replaced by xj dash and xj dash minus xj double dash, but this xj dash and xj double dash can take only positive values. So this xj dash double dash and xj dash will come in as decision variables in our what in our constraints, which are replaced uh, which replaces xj. Okay, so that standard form of LPP is obtained. Okay, now, so that's about the second case also. So now we have studied how to convert, if the problem is not in standard form of LPP, then how to convert it. Okay, so then the next case is associated with our constraints. That means what we will do, if the constraints, that means m number of constraints are not in the standard form of LPP, then what we will do? That is our next question. Suppose if a constraint appears in the form of less than or equal to type inequality, that means the expression contains less than or equal to, okay, some, that means a11 x1 plus a12 x2 plus etc plus a1n xn is less than or equal to some b1, like this. This is the constraint. Okay, so clearly we can say that this is not the standard form of LPP, because the standard form of standard form of LPP characteristics is that all constraints must be in equality form. But here we have an inequality constraint, that is 2 less than or equal to. Okay, less than or equal to. So what we will do is we will convert this inequality constraint form, into the equality constraint form by adding a non-negative variable, that means a positive variable, a non-negative variable called slack variable, that means something here, something on LHS, the LHS is less than RHS. Okay, that means something less than something, that means, for example, we have yes, we have two numbers of God, and we have four numbers of course. We are taking these two examples. Then these two numbers of God is less than four numbers of course. This is very clear. So something less than something means you have to add this two numbers of God plus two numbers of God again here, so that this constraint will be becomes equal. Okay, so such a non-negative variable, adding a non-negative variable, and that uh, in order to make it equal. Okay, so such a variable is known as slack variable. Okay, so that means we have converted the previous this yes inequality constraint, which is not in our standard form of LPP. We have converted it into standard form by adding a slack variable called slack variable slack variable. Let us say it is xn plus 1. Okay, so our constraint is converted into standard format like this: a11 x1 plus a12 x2 plus etc plus a1n xn plus xn plus 1 is equal to. Now we can happily, or we can without any doubt or fear, you can write it as equal. Okay, equal to b. Okay, so that means we will introduce another decision variable xn plus 1 here, xn plus 1. Okay, so that it got equality form. Okay, so that is about this case. And also we have another possibility, this a11 x1, the same and or suppose any other constraint. Let us say arbitrary, we can say ak1 x1 plus ak2 x2 plus etc plus akn xn is, suppose it is appeared as greater than or equal to some bk. So this is p1. Okay, bk. Okay, so in this case what we have to do is, let us go back to our previous example, that is two numbers of God less than four number of forces. Suppose this case appears like this: some six numbers of God, which is greater than some three numbers of force. Okay, this is same as our this equation, inequality constraint, right? So what we have, yes, so in this case, in order to make this equal, what you have to do is you have to subtract, that means minus, you have to subtract three numbers of God on LHS, so that equal to sign can be without any doubt, you can what equate it, right? So what you have to do is you have to you have to convert this inequality constraint into the standard form of LPP, that is you have to convert this greater than or equal to sign into equal to sign. So what happens is I'm subtracting a variable, another variable, that is known as surplus variable, surplus variable, surplus variable, and it is another decision variable, that is xn plus 1. Okay, so what happens to our new uh, constraint is converted into the standard form like this: ak1 x1 plus ak2 x2 plus etc plus a kn xn minus xn plus 1 equal to pk. Okay, so this is converted into the standard LPP problem. So okay, that's all about it. So uh, yes, this is uh, uh, all about our conversion of a yes, a objective function or a minimization problem or a maximization problem, actually a problem which is not in a linear programming problem, which is not in standard form, that can be converted using the three ways. You can apply the three ways so that you can convert it into standard form. Okay, so once you convert it into the standard form, then you can solve it by following some usual steps. Okay, that we will discuss. Then before discussing that, you have to you should be familiar with some terminologies again. That means if once you the convert your LPP into the standard form, then the next step is to solve for the variables, decision variables. You have to you should get the solution for it. So before getting into that some more terminologies we have to discuss. That is, first one is feasible solution. What do you mean by a feasible solution? Feasible solution means in a linear programming problem, any solution that satisfies the constraints ax equal to b and x greater than or equal to 0 is called the feasible solution. Okay, in a LPP, any solution that satisfies the constraints ax equal to b, that means standard form, and x greater than or equal to 0 is called the feasible solution. So f of x, this minimize f of x, then this we will get some solutions. So if that solutions also satisfies the given constraints, that the solution is known as feasible solution. Okay, then the basic solution is one in which n minus m variables, if n greater than m, are set equal to 0. A basic solution can be obtained by setting n minus m variables to 0 and solving the constraints using that. Okay, so that is also okay. Then we have optimal solution. A feasible solution that optimizes the objective function is called an optimal solution. Okay, then we have basis. Basis means the collection of variables not set equal to 0. the collection of variables not equal to 0, that is non-zero collection of variables. To obtain the basic solution is called the basis. The basic feasible solution, basic feasible solution means a basic solution. It is a basic solution that satisfies the non-negative condition. Okay, then it is called basic feasible solution. So these are some terminologies, though, so that's not that much important. So what we will do is we will move on to the problems, linear programming problems. Okay, and we will discuss that. Okay, so this is our introduction.